Hello and good afternoon, everybody. Thank you for joining today's
Recording
webinar.
In progress.
Yeah, thank you for joining today's webinar. I'm Andrea. I'm your chair today. And for this webinar offered by the ARC Energy Efficient Separation Hub, Monash University, the Monash Center for Membrane Innovation, Monash University, and the Membrane Society of Australasia. Today's presenter is Professor Qing Yang. So before moving to Qing's presentation, please remember to please mute your mic during the presentation. And if you have any questions, please just drop them in the comment section. So we welcome today Qing. Qing is an associate professor in the Department of Chemical Engineering at the University of Leuven in Belgium. Qing recently actually moved to Belgium. Before she actually spent 6 years working in Australia after graduating her PhD from the Nanyang University in Singapore. So Qing worked in Australia between mostly at Victoria University and then Deakin University as a senior research fellow and lecturer. So Qing has more than 10 years actually of its interdisciplinary research conducting on functional membranes for hybrid separation systems, for resource recovery, bioseparation, and water purification. And she has a great expertise in actually combining experimental and multi-scale numerical modeling and applying directly to a real system for water treatment. She also currently the editorial board member of the Desalination Journal, and also an early career editorial board member of the Journal of Membrane Science. So please welcome Qing, and I'll let Qing start the presentation. I'll stop share. You're on mute, Qing. Qing, you're on mute.
Sorry.
Okay.
Yes. Unaware. Okay, let me move this here. Hello, thank you, Andrea, for your kind introduction. And great to see everyone. Great to feel. I feel that I'm back in Australia to see my Aussie colleagues, and of course other participants from all over the world. Thank you very much for inviting me to give this presentation. And today, I'll be sharing with you a little journey through how we, excuse me, how we basically use the process intensification strategy to design a membrane process for efficient separation. And particularly, I use membrane distillation here as an example, and also related to its applications in the resource recovery. So this is the outline of the talk. So firstly, I introduce membrane distillation, if you have not heard it yet, and also its applications in the resource recovery. And then followed by, as I mentioned, our journey through using that process intensification to actually understand the fundamentals and to help us to design a system. Lastly, the concluding remarks. So why are we, as a membrane researcher or as a person who works on separation technologies, we understand that the limitations or the problems with the current environmental and sustainability issues, and particularly for the regarding the water recovery, Australian. The Australia side is a good example because it's a very dry country, and we need to broaden our water resources by through finding sustainable solutions. And also on the other side, if you look at the mineral and energy resources that we have today as compared to 50 years ago, so as we can see that the depletion is going very scary, and if you don't sustain the consumptions, and it's going to be very dangerous, and therefore developing really recycling technologies and looking at the circular economy solutions are really the way to go to conduct or to bring the waste to the products. This is actually a global initiatives. So now today, as I mentioned, I would like to introduce a bit on membrane distillation and how it is being positioned in the resource recovery industry, or more in applications. So membrane distillation, it is a thermal-driven process, as many of you have been aware of. So it is only allows the vapor to transport. Let me share my pointer if I could. Yeah, so it allows the vapor to transport through an unwetted membrane. In a sense, the bulk membrane is hydrophobic. So, and there are many applications of that. The membrane distillation has been studied or investigated for over 60 years now. So many applications such as water, minerals, metals, nutrients, and macromolecules such as proteins. So membrane distillation started on the competing position with the reverse osmosis, and it basically failed. And then slowly in the last decades, I would say slowly finding its position in resource recovery. So there are a few configurations of membrane distillation, including direct contact, vacuum, air gap, and sweeping gas. And there are many more that originated or variations from this original configurations. Okay, so there are many benefits of membrane distillation as compared to pressurized membrane processes such as reverse osmosis and nanofiltration, because it's non-pressurized. Theoretically, it has 100% rejection to the non-volatiles. That's why it makes completely pure distillate. And also because of its insensitivity to the or to the solute concentration, and that makes it an ideal solution to deal with extreme concentrations. And that's why it's being positioned in the resource recovery. And that's why it's also faced a lot of challenges. And another beauty is it could be integrated with low-grade waste heat, and that means it doesn't rely on high-grade thermal energy, more looking at waste heat and also low-grade or renewable energy. So as I mentioned, in a previous MD was trying to compete with reverse osmosis or other desalination technologies, and then it didn't really succeed in finding a position in the industry. And nowadays, if you look at what we are in the society now, the current practice is we are disposing the waste from the industry or from the plants, actually that creates a lot of CO2 emission and also creates a lot of liquid and solid waste. That the current trend is really to look at technologies that can actually help to close the loop to recover whatever resources from those wastes as much as possible. And membrane distillation is one of those technologies. So membrane distillation, the unit itself, as we already mentioned, it's very versatile. It can be used for recovering many solutes, and it has been using in combination with other technologies. As we mentioned, it deals with high concentration, therefore it has to be positioned somewhere in the process trend. So it has been, for example, integrated with the reverse osmosis and nanofiltration to be at the high concentration end, and coupled with the membrane crystallizers to actually produce minerals, and at the same time maximize the water production. And it has also been coupled with the adsorption and extraction to recover or remove the metal ions or metals. So it has also been coupled with the full osmosis, like Sean is very familiar with for sure, so that to recover the nutrients in many different ways. Also, in terms of recovering the energy, blue energy, particularly for water, it has been coupled with reverse electrodialysis and pressure retarded osmosis. So it's a very versatile technology or process. And it has to be, together with integrated with other systems. As I mentioned, so as we mentioned, there are many benefits of membrane distillation, but there are also drawbacks. Such from fundamental point of view, membrane distillation is quite different from other membrane processes because it combines heat and mass transfer, which makes it extremely challenging in terms of talking about thermal efficiency. So there is heat loss in the process, there is intrinsic heat loss. And also because there is no particular commercial membranes particularly designed for membrane distillation, and it is struggling with the throughput and pore wetting issue, because particularly when you talk about dealing with high concentration solutions, and this becomes a serious situation that we have to find a suitable membrane for it. So therefore, if you look at that the framework of developing a viable MD process or MD system for resource recovery, we have to look at, okay, do we understand the transport mechanisms enough to understand what are the limiting factors in preventing it from performing well, and also the membranes, do we have the ideal membranes, and also look at more synergistic point of view, the energy efficiency. So therefore, in the past years, we have been looking at developing a multi-scale process intensification strategy to design energy efficient membrane systems. So today I will be more talking about fundamental methodologies rather than applications. So yeah, of course, there are a lot of applications so we have been working on. So before that, I would like to remind you a bit on the concept of process intensification. And process intensification refers to making changes to manufacturing or processing designs for substantially improving its energy efficiency and cost-effective or enhancement of other qualities. So basically, in the last decades, and that paradigm of the process intensification has been shifted. So this is developed, the concept has been developed by one of my colleagues in the University of Leuven. So basically, if you look at from different perspectives, from the scale point of view, the PI strategies goes from molecular level to systematic level, which is more on, a plant, a chemical plant. So therefore, the membrane or membrane separation process, it fits very well into this and the whole across the scales. And the approaches that we are taking includes the spatial domain, which is looking at the structure, and the thermodynamic domain, which is looking at the energy and exergy part, and functional domain, which is looking at the synergy interactions between solutes and surface, for example, and time, which is the temporal domain. We're looking at the kinetics and dynamics. So now coming to what we have done. So as I mentioned, we went really from micro to macro level. So that on the micro level, the strategies that we have been using is to uncover the complex transport mechanisms and to really identify, okay, what is the limiting performance limiting factors, and then we can design the system accordingly. So we call that rational design. And it also happens to when designing a membrane. So we know what kind of membranes that we will need for such application, and then we come up with strategies to overcome the low effective needs, such as low flux and the pore wetting issue. So together with the understanding from these two perspectives, then we can design a membrane module. So on a system level, we design. We also use the PI strategies to design a system to overcome the low energy efficiency and achieve technology piloting. Yeah, so on the first strategy, we basically use numerical modeling to understand what is the transport limiting factors and how we can improve the system. How do we design the membranes? As far as we know, in membrane distillation, as mentioned, that is a combination of mass and heat transfer. And also there's a boundary effect that is critical for determining that polarization conditions. So these were not described well by empirical models, and particularly in the context of high solute concentration. So, and later on, I will explain a little more. So if you look at the heat transfer models in membrane distillation, that that it consists of several parts, the heat input in the bulk, and when it goes through the membrane, there is two parts. one is the latent heat, the other one is the conductive heat. What the conductive is intrinsic loss of the thermal energy here. So therefore, although we try to maximize the latent heat utilization, it still exists as the thermal efficiency. It's a very tricky part to be improved. So when we first started off, as mentioned, we tried to overcome the limitations of the empirical equations. So we developed a two-dimensional heat transfer CFD model, computational fluid dynamics, to basically couple that latent heat and combine the Navier-Stokes equations to really identify. So what we did here was to include a sink term into the energy conservation equation to reflect the changes brought by the latent heat. So we were able to visualize the temperature and velocity and heat transfer coefficients, the profile, so that they can help us to determine, okay, what are the actual driving force. In mentioning that, I mean, this methodology is applicable to many other membrane processes as well. So basically, that understanding of the liquid solids, liquid boundary layer conjugate transport could help us to understand how we can design a membrane, or how can we design a membrane module. And also that model that we developed has really improved accuracy in prediction. So later on, we developed a three-dimensional CFD model to really look at, okay, so what are we identify in the first piece of work that the flow dynamics has a lot of influence, and how are they influencing how we can improve the module design to reflect that. So we design the modules in a way that it can include some turbulence buffers or turbulence promoters. And it turns out it could be quite substantial changes. The heat transfer coefficients is being improved by 6 times or so, and mass transfer coefficients 3 or 4 times or so. And then we also went on to designing a surface microstructure, because it is so essential in developing the micro hydrodynamics on the surface. So it turns out to be quite substantially contributing to the heat and mass transfer, and also reduce the energy uses for combining all the benefits. So interestingly, there are many concepts, or there are many experimental works developed later on as the technology is being evolved. For example, the pattern surface, the 3D spacers, and this have actually been designed to do the same thing. So it's quite interesting. So as mentioned, we are working very much in solid recovery or resource recovery, and that fact we're dealing with high concentration or near saturation situation is it is a challenge. It is particularly in hypersaline processing. So the influence of the saturation and solute transport behavior while the dewatering is going on, this is really not well understood. So we develop a model that's actually help us to predict the temperature and concentration profiles. As I mentioned earlier, concentration polarization was ignored in membrane distillation back in maybe 5 years ago. So we decided to look at this again and to look at, okay, whether concentration polarization has influence, and it does quite significantly influence, in particular when you're looking at near saturation. So we also develop model to actually help us to predict in terms of where we are in terms of the solute concentration and what kind of flux we can get. So we develop an exponential decay function that can actually help us to predict a range of membranes depending on where this concentration of the solute sits, and then we can define what is the relative flux as compared to its initial flux. And then we use this to map the concentration polarization coefficients with the hydrodynamics to identify, okay, what are the hydrodynamics that we are looking to operate the system more sustainably. So with this in mind, we have done a bit on crystallization. So in the membrane crystallizers, back in a few years ago already. So we started a few years ago of crystal growth on the membrane surface is controlled in terms of, crystal size, uniformity, and the time, which is the kinetics part. So quantification of crystallization on the surface was a big challenge. So we developed a model to actually combine nucleation and crystallization behavior into the mass and heat transfer modeling of MD. So this is a COMS model we developed. We call it COMS model is actually crystallization of membrane surface model. So that can be, coupled with the crystallization kinetics can help us to predict, okay, when the nucleation is happening, and how much yield of the crystals that we can actually achieve. So in this operational process, of course, we identify a lot of issues. We try to implement process intensification strategies such as redesigning the membrane configuration and also introducing bubbles, two-phase flows, and to really delay that occurrence of the critical flux. And the concept of critical flux was first proposed then really back in 5 years ago or more so. And then we were able to this is before we actually couple a crystallizer into it, right? So this is more looking at the MD itself, and a critical flux actually occurs anyway, regardless of what PI strategies we use. And then we design a continuous MD crystallizer system to actually control the critical flux situation while continuously designing or producing crystals, and we can control the crystal size depending on the operating conditions and the yield of it. So it's could have quite substantial influence on when you design a crystallizer that produces a polymorphs, crystal forms of desire. So later on, because we understand that in order to have a sustainable sort of operating condition, and if we have to have, if we can design an external crystallizer, the fact that we discovered a couple of years ago is, although it has a crystallizer and the flux decline was still quite substantial after a certain period of time. So we now in more recently, so we develop a models to really look at okay, so what is the nucleation? We combine the nucleation work into our MD model, and just to see, okay, when the nucleation is happening and how we can avoid it from happening. So we proposed this concept called critical Reynolds number or critical hydrodynamic thresholds. So basically to define operational windows of MD, to look at where we are, how we can avoid it from happening. So basically that can give us a safe and conservative operational window. So it's quite an interesting work. And recently we have developed a crystallizer for active pharmaceutical ingredients. So that actually, that work was quite useful in helping us to design the operating conditions. So it has quite a broad application. So as a summary for the first part, so we have gone from micro to milli level intensification, really starting from the molecular transport to designing the hydrodynamics. So we identify the hydrodynamic thresholds in operation, and that help us to identify what are the limiting factors, what are the key dominant factors in designing a system. So that help us to design membrane modules, and also help us to design arrays of membrane modules that can achieve crystallization. So, and as I mentioned, crystallizers design, and even it goes broader than minerals. It goes also to API productions, and it can help us to control the polymorphs quite easily. So the second strategy I'm going to share is more on the milli level when we look at the pore side or pore structure engineering. So if you were to intensify transports in membrane distillation. So as many of us know, there is no commercial membranes developed for membrane distillation, and they are facing bottlenecks in terms of the low process throughput and the pore wetting issues. So we started a few years ago looking at, okay, what do we really need to have for membrane distillation. In terms of the characteristics of MD membranes, it needs to have high porosity, highly connected pores, and has to have low pore size distribution and high liquid entry pressure, so that can resist the wetting. So we developed a new method. It's called non-solvent thermo-induced phase separation. So that uses water-soluble diluents, CPL, and also this is looking at PVDF fabrication, lower the fabrication temperature to 130 degrees. So basically, usually it's around 180 or 200. So, and we develop a PVDF membrane that has a very interesting asymmetric structure. So it has a relatively dense skin layer, so, and very thin. And that the bulk membrane has a very continuous, highly connected pore structure, contributing to the high porosity. So we call this single layer PVDF N-tips membrane because we're going to compare it with a dual layer. So we compare the performance with other membranes in the literature, and I'll do that a bit later. So the membrane performance was really the flux was the highest at that time, and also liquid entry pressure was 3.5, very ideal for membrane distillation, and the flux was quite high as compared to other data. So porosity, as we mentioned, we were able to achieve about up to 86 or even more, depending on the optimization of the fabrication conditions. So and then we went on to discover, or we looked at the mass and heat transfer trade-off relations in membrane distillation. And of course, if we could reduce the mass transfer resistance by reducing the thickness of the hydrophobic layer. However, if you look at the heat transfer, if we were to have a thicker membrane, that they can reduce the heat loss. So we designed a dual layer membrane as a hydrophilic dual layer membrane with thick enough that is supported by the hydrophilic layer. So it does not compromise the mass transfer coefficient or resistance. So in this case, we designed a dual layer membrane is consisting of a PVDF hydrophobic layer and PVDF PVA hydrophilic layer. So as you can see here, the transition between hydrophilic and hydrophobic layer is actually very smooth and very interesting. The top surface is still a skin layer, and the cross section shows the top part of the membrane shows a finger-like structure, and this is the hydrophobic PVDF bulk PVDF layer, and the bulk membrane is still having continuous pore structure that is attributed to the N-tips formation kinetics. So basically, it reduces the hydrophobic layer thickness quite substantially. So and another factor that we look at, I'll share the results of this membrane a bit later, but really going forward for the next generation of the membrane that we design is to really substantially improve its mechanical strength and also the anti-wetting properties. So we design a fabric embedded membrane also through the N-tips methods. So this is to really substantially increase, and we found there are some interesting phenomena in this process, because when embedding the membranes, embedding the fabrics into the membranes, and then we found that is quite an interesting, we call the pseudogenous structure is being formed. So basically that reduces the mass transfer resistance quite substantially on one side of the membrane, and so it still was able to achieve very high permeability, and the mechanical strength was 23 times higher than a normal pure PVDF unsupported membrane, which is and we applied that in a concentration of MSG until crystallization, and the performance was easily recovered. So and trying to compare the different NTIPS membranes that we develop, and of course there are pros. So there are actually differences in these membranes, and as you can see, the dual layer membrane has the most much higher fluxes compared to the other membranes, and we're comparing this one as compared to literature data. A flux of literature membranes reported in the literature, and for the single layer and the embedded PVDF membrane, so that the flux is lower, slightly lower, but still higher than the literature data. So, and of course, there is still some optimization that needs to be done in that space. So to summarize the second part, so when designing a when we're trying to engineer a pore structure of a membrane, so we come up with a strategy to control the pore structure and how that will help us to facilitate a transport and eventually help us to achieve energy efficient separation. So that's more really looking at formation kinetics of membranes. So the third strategy is looking at a system level, systematic level, looking at how the MD can be integrated and what are the potentials that can be integrated with other units. So that's for value recovery and also zero liquid discharge applications. So, and of course, there's a lot of discussions on how we can bring that the laboratory work to the field or to pilot studies. So as we know, one of the key things in membrane distillation is a low energy efficiency and how we can, through designing integrated units that can help achieve more efficient integrated systems. And this will help us to do the upscaling a lot more efficiently. So as mentioned, that thermal efficiency MD is really is influenced by the intrinsic conductive heat loss. So how we did in the beginning is we try to integrate a heat recovery unit into that, so that basically can help us to recover some heat. So one of the parameters we use is to identify or to evaluate the performance is called gain output ratio. So GOR. GOR is looking at the ratio of the latent heat being fully is being utilized and versus that total thermal input. Right, so the higher the GOR, the better. So we develop or we use a full factorial design strategy to actually help us to understand what are the dominant parameters in this process, and then that can help us to identify to improve the thermal efficiency accordingly. So as a matter of fact, that in the literature, the GOR of most membrane MD systems are below 1. So by identifying the key parameters, we improved that. Based on that, the GOR could go below above 6. So basically what we did was to identify the most energy concerning factors in this process. So as a result of this study, so we develop an implicit GOR correlation, and then can also help us to understand the nonlinear scale-up relationship in this membrane distillation. So when dealing with the MD crystallization, we did some fundamental work in the beginning. We tried to identify what are the most energy consuming elements in this MDC system. So we identify MD itself is quite it's very energy intensive. So then we incorporate the MDC system with the heat exchange unit that changes the spectrum quite substantially. So, and then we utilize the methodology to design larger scale MD systems. So to basically to look at whether if we were to increase the membrane areas, we were to increase to include multiple membrane modules, and how are we going to design them? So it turns out that if you arrange the units in parallel, is more energy efficient than the arrangement in the series. So it becomes more dominant when you increase the scale of the membrane units, membrane systems. So just to give you an example on I haven't been talking about applications a lot. We have done quite some work also on nutrient recovery, on ammonia recovery. So we before, when I was in Australia, we were able to do a pilot demonstration on to integrate MD with a struvite precipitation. To recover the nutrients from municipal waste. So we were demonstrating 90% of the nutrients could be removed with 80% less energy. So this is a work supported by Intelligent Water Network. So this is actually our piloting container on site, and with the nitrogen removal and the phosphorus precipitator. So this was just briefly going through the performance in various operation modes that are happening on site. So, and also with the relations with the feed characteristic that you found. There are a lot more results. So we actually still drafting up the paper. So a summary on the systematic level that we're able to implement intensification strategy as well. So to really identify how we can integrate and how we can improve the energy efficiency of the system. As I mentioned, membrane distillation is really sitting in a spot that can connect other units, to a practical application to recover resources, and it's a rather versatile technology. So finally, as a conclusion, I would say through our journey, we use numerical analysis to understand the molecular transport and to really identify what are the limiting factors in MD. So that can help us to reduce experimental efforts quite substantially and provide strategies to identify performance or to really intensify the performance at high concentration. And it goes beyond minerals to many other solutes. And in saying that, the concept of critical flux or the operational thresholds are still underdeveloped in MD. So we are the first to propose that, but still there's a lot to study. Secondly, it's on the membrane formation. So we can manipulate that formation kinetics to actually obtain asymmetric structure, so that can actually produce a desirable performance in MD. So, however, in terms of the long-term operation performance, we still need to work on surface intensification, perhaps to further improve that. And lastly is on the system level integration. So how we can integrate operation units and parameters to intensify the energy efficiency of MD systems, and how we can incorporate a heat recovery into that when the non-waste heat scenario is not available. So, and of course, as I mentioned, on the practical level, there is a lot of efforts in finding a spot in industry for resource recovery, for membrane distillation, and many researchers working on that apparently. So that's very much all for my presentation. I would like to thank my students and colleagues in the universities that I work before, so including Nanyang Technological University, Victoria University, and South China University of Tech, and also Ningbo University and University of Leuven, and also my mentors along the journey. And also I would like to thank the funding agencies that fund our research. And this is a picture of our Ehrenberg Castle in Leuven. So it's a very beautiful place. If you ever stop by, if you ever, come to a conference in Europe, you're more than welcome to visit us. And lastly, because our group basically formed during COVID, so we don't have a group photo. So I have to share the photos of individual colleagues, individual students. So basically, this is the structure of our group. So we, other than joint students, I still join and supervise with my Australian colleagues. That the other two clusters I have in Leuven are on the ion separation and also bio separation. So with a couple of postdocs and PhD students and master students. So we do also have opening every now and then, particularly on the modeling side. So if you're interested, feel free to send me an email. That you have the email address here. All right, thank you very much. That's very much for my presentation.
Professor?
Yes?
Thank you so much for this very informative. I am Muhammad Sultan from Hubei University, Wuhan. I'm a PhD scholar, and my research area is photothermal based steam generation. So it was very informative. I have few questions about this presentation. The
Okay.
first question in second work about PVDF.
Yes.
So, as we all know about the toxicity of PVDF, so how you cope this toxicity and you're using in membrane? So, I was a little bit confused in that. The
Mm,
second question is MD system promote zero liquid discharge phenomena? I mean, we are working on photothermal driven steam generation or seawater desalination.
mhm.
So we are not using any input energy. We are using just solar energy. And we design evaporation structures that float on seawater. So we claim, and we also perform in our group, some zero liquid discharge phenomena. So is MD system also possess zero liquid discharge phenomena? That's all,
Yeah.
Losh.
Yeah. Okay.
Maybe you
Yeah.
want to
So
go
I.
one question at a time, Ching. There are two questions,
Yeah.
so
Yeah.
yeah.
Of course. Okay. So the first is PVDF. The second is zero liquid discharge. Yeah, maybe I answer your second question first. So as far as I can understand, so you are asking whether membrane MD can also perform zero liquid discharge. Yeah, so that the answer it is yes. It depending, of course, which configuration that you use, and has been demonstrated already in the literature. So it could actually maximize or completely remove the water component from a solution. So well, the solar evaporation is a different technology. They were relying on the natural sunlight, and while the a membrane system is more modular, and yeah, there are pros and cons. I wouldn't compare apple to orange in this case. So yeah, so they're both capable of doing that. Um, on the PVDF membrane, the toxicity of that, yeah, I don't think I'm not able to answer the question in a good way because it is a debatable point. But PVDF itself, yeah, yeah, so I think we are looking, of course, developing more greener um, solvents and greener polymers that possess, you know, biodegradable properties and you know, less fluoride. So I mean, you're right, and it is going forward. We really will be developing. However, I mean, in terms of the strengths of the conventional polymers, we still have to admit they have the advantage. So this of course it is it will be studied.
Thank you so much. Thank you so much, Professor.
Yeah, no worries. I lost my
Thank
video.
you. I think we have another question from Yusak. Um, as shown in your early slides, when using the surface micropatron membranes, why is the heat transfer coefficient enhancement more pronounced, sixfold, as it is compared to mass transfer coefficient? Is there any reason behind it?
Hmm. Okay. Very observant. I guess this. I guess this is not. It has to do with a particular feedstock that we use. I guess if you were to, the magnitudes are different. If it depends on. I mean, I guess if you were to use a concentrated solution in this case, the mass transfer coefficient might be less. prominent than what you have now, or maybe more as compared, because it depends on the initial magnitudes that you start with. Yeah, so I think that heat transfer is more also to do with the temperature conditions that we set at that time. I believe there is a variance in there. So if you change your inputs, and that might change as well. And it has to do with the hydrodynamics, the influence to the hydrodynamics, the influence of the hydrodynamics to the heat transfer that is more prominent at that conditions that we use.
I hope this answered the questions. Otherwise, Yusak, please feel free to answer in the chat. We have another question from Hadi. Hadi is asking if you ever done any research on pore modification of MD membranes using electrolyte material. And this question is about more the use of ionic liquids for them to modify actually the pore, and I guess towards pore engineering. Have you done any work on that?
To incorporate ionic liquids into the membrane? To incorporate, is it?
I guess to modify, probably to tune the pore, the porosity and the pore size.
No,
maybe Hadi can be more specific in their question.
Yeah, ionic liquiding in tuning the pore size. Maybe you can explain a bit more. Okay, yeah, okay, I can see that in chat. I can read it. We haven't done anything on that, but it is, yeah, it is. I guess it is possible. And then, as I said, there are some researchers looking at green solvents, you know, including the additives and green polymers that can actually be the next generation membrane. This is looking at the future. Yeah, but we haven't done anything on that.
Any other questions?
I lost my.
Yeah, can I ask one question?
Yeah.
Yes.
Yeah. So thank you for your talk. I'm just thinking about the proliferation. So you talk about the membrane distillation. So, and then so how do you compare the proliferation membrane with the MD? So I mean, any potential, you know, application for those, you know, you have just talked about?
Evaporation, it's a good question. We also do evaporation. So, and we also just develop a evaporation crystallizer unit. So it is capable of crystallizing, and the fact, I mean, evaporation has been quite very much positioned in solvent or you know, that what do you call dehydrolyzing the solvents. But now there are some attentions to bring the evaporation to desalination, but I think it's not the right way to do it. It's a similar to what MD was in many years ago. So now I would say evaporation in terms of resource recovery, it also has the potential, and in fact we have worked on that. So it has also the benefits of dealing with high concentration. So, but it's rather, compared to MD, I think it's still less developed in terms of how the membrane itself will interact with those crystals. This is less developed. We found there are some quite quite challenges in there when you have the crystals form.
Yeah, okay. All right. Thank you.
Yeah. Thanks.
Thank you. Thank you, Wenting. I think we have a comment on the chat for you, Ching.
Yes.
It's more of a comment than a question. I have a quick question. Your presentation was very interesting. You included many different aspects of your research, and I'm quite fascinated by the holistic approach that you have in your research. So going from spanning computational modeling, the study of like membrane system or pore engineering, and then the final process optimization. So that's a very comprehensive approach. My question regarding MD is, what do you think is in this, considering all these aspects, right? Where do you think we can find the real bottleneck for MD at this stage? Is it more towards like surface science? So it's wetting their bottleneck? Is the module design the bottleneck? Is some fundamental aspect in mass transfer or heat transfer that not well understood that they represent the bottleneck right now? So in which areas do you think, do you see room for improvement?
I guess from every perspectives, and I think I mean, as mentioned, that we have probably developed MD for desalination in the same position as reverse osmosis, and there was a lot of systems or modules, membranes that were developed based on that requirement. So when we go forward to what we are really at, where we are really at now for resource recovery, looking at very tough situations, and it does, I mean, the wetting issue and also the module design, it has to be rethink. And that's why, I mean, that as we propose about the critical thresholds of the operation, that bottlenecks, yeah, I think it's everywhere. I mean, in terms of talking about fouling. So for example, the fouling was not really considered significant in MD maybe, a couple of years ago, but then when there's a review paper by Sean, I think Sean's group, couple of maybe 6 years ago, came out, and it was summarizing, analyzing all this fouling issues identified in MD, and then afterwards it became a trend of operation, a trend of research. So I think it's in terms of the bottlenecks, finding the right membrane, and then has the really strong anti-wetting, because particularly concerning about high solute concentration in this case, I think it's extremely difficult. And so I think that the throughput or the permeability of membrane is probably less of a concern if it could be sustainably operated. And the modules, talking about modules, is more about how you can separate the solids and the liquids if you were to design like a high concentration system, right? It's a very interesting subject. And talking about integration, system integration, there is a lot more potential and possibilities in integrating MD into that in various of applications. Yeah, hope that answer your question. There's no really a direct answer to that. But yeah, it is fascinating research as it is because of the challenges, right? But in going forward in industry application, I think it depends. It varies from application to application.
Thank you. I think it's a very insightful answer. I think we have time for one final question from the chat. I don't know if you can read it, Sheen.
Okay, I have
from Bahai. A key premise of the presentation appears to be the new theoretical announcement to MD. In terms of actual applications, the only demonstration data presented, Pilet Demonstration 1, appears to be from an unrelated project predating the current studies.
Not sure if I understand.
I think it's related to the slide where you presented the pilot plan.
Yeah, I wouldn't say predating. I mean, of course, it's on volatile recovery. It's a different application, but the way we operate the system is still a lot to learn from the previous studies in terms of the operating conditions, in terms of we also, I mean, in the studies I have discussed previously on the fundamental side, we also study vacuum membrane distillation, which I did not, specifically elaborate on, but there's also, yeah, a lot that we learned on in terms of how we can enhance the volatile recovery, in terms of setting the right operating conditions, in terms of, how we arrange the equipment. So yeah, I wouldn't say it's irrelevant, but of course, minerals we have done quite a lot on the fundamental level, just to show that membrane distillation has a perspective to go from bench to the pilot.
Yeah.
Yeah. Okay. Hope that answers your question. Thank you.
Thank you, Ching. It's almost 5, so I think we are running quickly out of time. If we don't have any other questions, I would like to thank you, Ching, and everybody for joining the webinar today. I just would like to share one final slide, if you can.
Yeah, I stop share.
Yeah. So I just would like to share. Yep, I hope you can see my screen. So in terms of next events, we have basically one webinar per month. So next webinar, we'll be hosting Professor Faisal Hai from UOW, from University of Wollongong. And then there are also 2 other webinars scheduled by the end of the year. And also don't forget about INSEC 2022, the membrane conference that will be held in Melbourne in December 2022. The abstract submission is open, I believe. And also you can visit the website actually to get a bit more of information about the event and the committees and the venues. And I thank you again, Ching, for joining us. And I thank you all for attending the webinar.
Thank you.
And I wish you all a very good afternoon or the rest of the day, Ching. It's morning there in Belgium, so you have the full day ahead. Yeah.
Yeah. All right. Thank you so much.
Thank you.
Thank you, everyone, for your
Ching.
questions. Yeah. Thanks. Yeah. Bye-bye.
Bye.
Thank you. Bye.
Thank you. Thank you, Celine.